We just got done talking about the driving forces and whether or not we can predict if a reaction will happen spontaneously. So now we're going to talk about activation energy and catalysts. So when we talk about reactions, we need to understand that molecules must collide at correct orientations and have enough kinetic energy for a reaction to happen. So we must, in order to form bonds, we've got to break bonds, which is endothermic. So for most reactions, it takes energy to get the reaction going, and we call that activation energy. So forming water bonds is actually, in total, exothermic. And once we've started that exothermic reaction, that energy that has been released actually activates other molecules, much like a domino effect. So activation energy, which is denoted capital E with a subscript of A, so the activation energy, is just the minimum energy required to get a reaction going. And it's to get to the activated complex. And we'll actually talk about what that is in a minute when we talk about the activated complex. So here we're just showing the reactants and the products. And here where my reactants start to get to the activation complex, which is up here on any energy hill graph, the EA is just the energy required to get to the activation complex. How I can measure my total change in H, or my total change in energy, is to look at the difference between my reactants and my products. And so this is just showing the total change in H based on where those things are on the graph. So activation energy is the energy required to get to the activation complex. And the activation complex is a transition state of breaking and forming bonds. And you guys have actually learned about the activation complex already when we wrote our activation energy diagrams when we did the water lab, the making water lab. This was one of the post-lab questions, was to draw a graph showing the molecules as a reactant when they were shown breaking up, and then also as a product. And so now we're going to put that back into talking a little bit more about the thermochemistry of it. So again, the activation energy and the activation complex. The activation energy is the energy required to get to the activated complex. That complex is going to be shown at the top of the graph. When we look at the energy of the reverse reaction, we call that EA with a subscript of 1. So that's the energy needed to reverse the reaction or to go backwards. And the total change in E, or the delta E, is just the net energy change in the reaction. So those are some labels that we'll use on our energy graph. So let's go ahead and label this. So the first thing that we can label are our reactants and our products. So we can label those things. And I know that the energy from the reactants to the top is my activation energy, because that's the energy required to get to the activation complex. And I know that the energy difference between the reactants and the products is my total change in H. And I'm denoting that as a positive because I know that the products are existing at a higher energy level than the reactants, so it actually took energy for this reaction to happen. The energy of the reverse reaction is just denoted from where the products are to the activated complex. And then the top would be my activation complex. So then what I want to show you is how this breaks up where we're looking at just at the molecular level. So at first we start with reactants. So for example, if we're making water, we start with hydrogen and oxygen. And the energy added will help break up those molecules. So those molecules now are individual. The molecules are split apart. That takes energy. So remember in our making water lab, that energy was the flame. And it's just that transition in between bonds, again, is that activation complex. And then my products now are water. So it's just showing you your final product. So hopefully at a molecular level, that's making okay sense. So the collision theory assumes that the reaction, those molecules need to have correct energy and correct orientation in order for a chemical reaction to be produced. So those are two very important things. They will probably come up again at some point. So again, the correct energy and the correct orientation to produce a chemical reaction. And so there's 5 important factors for if a reaction is going to occur or not. So if it's going to happen. So the nature of the reactants. So it depends on the particular reactants involved and the bonds. So if something is soluble, or the activity series, talking about just what's happening and what is involved. The surface area, so more surface area is available, more things can collide, so thus the more the merrier. Temperature, so the hotter the faster the molecules move, and if the faster the molecules move, the more kinetic energy they're going to have, which helps with one of the factors for the collision theory. If the molecules are moving slower, they're probably not going to have enough kinetic energy for a reaction to happen. And then the concentration, the more molecules, the more collisions, and thus the more the merrier. And if there's more molecules, they're also probably more likely to have the correct orientation, as well as the correct energy. And then a catalyst. So just remember, a catalyst is a substance that changes the rate of the chemical reaction, but it is not permanently consumed. It is not a product, and it is not a reactant. What a catalyst does for us is lowers the activation energy with a different path. So if you remember from the types of reactions lab at the beginning of the year, we used sulfuric acid, and we wrote that catalyst above the arrow. So again, we show catalysts by writing it above the arrow. So reactants and products here, so with a catalyst, if I've got a reactant here, we know that we have an activation energy without a catalyst. But then when I show a reaction with a catalyst, that red line is showing that that activation energy is actually lowered with a catalyst. So it lowers the activation energy and allows that reaction to happen a little bit easier and probably a little bit faster with more products being produced. So there's the rest of our notes for the thermochemistry unit.